Okie dokie. So let's get started now. In this video, we're going to be solving June 2019 variant 1. So that's IGCSE Physics 0625 or 0972. Doesn't matter either way. This was a pretty challenging exam in paper 4. A lot of the questions were relatively tricky with a few annoying ideas. So let's just get right into it, shall we? Now, before we get started though, a quick hint about paper 4. Usually the questions in this particular paper show up in the order of the syllabus. So we've got 5 units in our curriculum, as you know, mechanics and thermal physics and waves and electricity and magnetism and atomic physics. The questions usually show up in that order, with the majority of the questions being either mechanics first, so 2 to 3 questions of mechanics, 1 or 2 questions of heat, 1 or 2 questions of waves, probably 2, then 2 to 3 questions of electricity and magnetism, and then a single atomic question at the end. That's usually how it is. Sometimes the exams don't follow that exact formula to the letter, but keep that in mind when you solve past papers though. So anyway, let's get started. Question 1. Rocket is stationary on launch pad. At time t equals 0, the rocket engines are switched on and exhaust gases are ejected from the nozzles of the engine. So, the rocket accelerates upwards. Cool. This figure shows how the acceleration of the rocket, I don't like the blue. So the acceleration of the rocket varies between time t equals 0 and t equals f. So as you can see, it's moving with constant acceleration. Nope. Increasing acceleration. This is an acceleration time graph. We don't see this very often. So acceleration increases and then it's constant. Cool. So first define acceleration. This one is easy. It's the rate of change of velocity. You could also say change in velocity per unit time. No biggie. Next. On figure 1.2, sketch a graph to show how the speed of the rocket varies between time t equals 0 and time t equals tf, with this particular change in mind. Now, take a look at this. This shows you that the acceleration is increasing. So let's just write this down, increasing acceleration. And then you've got constant acceleration. Now, just to quickly remind you, in a speed time graph or velocity time graph, increasing acceleration looks like this, and constant acceleration looks like so, which means the line is first going to curve upwards with an increasing slope because the acceleration is increasing. And at this particular moment of time, it's going to continue in a straight line. So we're going to curve upwards first. And then at this particular moment in time, we're just going to keep going straight. I tried to balance it out so that it's basically at the same point of time. Yeah, roughly. Okay, cool. So increasing and then constant. Next, sometime later, the rocket is far from Earth. The effect of the Earth's gravity on the motion of the rocket is insignificant. As the rocket accelerates, its momentum increases. State the principle of conservation of momentum. Again, this is a very simple definition question. So it simply states that the total momentum of a closed, isolated system is constant or remains constant. The word isolated system simply means that there are no other forces acting on the object, or you're just ignoring other external forces acting on the object. Next. Explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gases. Well, you need to imagine what a rocket looks like. So if you got this big rocket that's going to fly out, boom, and you've got exhaust gases being pushed out. The rocket is moving upwards, sure, but that's because of what exactly? That's because the exhaust gases are being pushed down. Because you're pushing the gas down, the change in momentum that the gas experiences is the same change in momentum as that the rocket experiences. That's why we need to burn that gas. That's why we need to force it out of that jet engine, because we need the gas to move down so that the rocket moves up with the same force and same change in momentum. So explain how the principle of conservation of momentum, meaning the total momentum is the same, or the change in momentum of the rocket is equal to the change in momentum of the gas, these should be equal. So we're going to first explain how the rocket moves. So the rocket moves upward with increasing momentum. Cool, because it keeps speeding up. That's fine. But what happens to the gas? So the gas of the momentum increases, okay, in the opposite direction, which gives you a total momentum of 0, by the way. So the rocket moves upwards with increasing momentum, and the exhaust gases are pushed downwards with increasing momentum by an equal amount. Or how about this? And the exhaust gases momentum increases in the opposite direction. Okay, I can't spell tonight. So that's what the 2 marks are for. Mentioning what happens to the rocket, it gains upward momentum or just increases the momentum upwards. And what happens to the gases? So the gases increase in momentum, but in the opposite direction. This is important, the opposite direction part. Okay, next. Figure 2.1 shows a sign that extends over a road. The mass of the sign is 3.4 times 10 to the power of 3. So let's mark that number down. Calculate the weight of the sign. Easy. So mg, which is mass times 10. So 3.4 times 10 to the power of 3 times 10. This gives you 3.4 times 10 to the power of 4 newtons. By the way, you can write your answers down in standard form, or you can just write the whole number down, but I prefer standard form, and so does the examiner. The weight of the sign acts at a horizontal distance of 1.8 meters from the center of the support post, and it produces a turning effect about P. Now, here's a hint. Whenever you see this about a certain point, about P, this is our pivot. This is a moment question. So as long as something is turning about a specific point, whether he calls that point A or B or P or whatever, that point is our pivot. P is a horizontal distance of 1.3 from the center of the post. Calculate the moment about P again, here's that term again, due to the weight of the sign. So that's also easy. Moment is force times distance. But which force? Well, he wants the weight of the sign, which is 3.4 times 10 to the power of 4. Cool. Times, here's the doozy. What distance do we use? Is it the 1.8? Is it the 1.3? Neither. It's 0.5. Why? Because this is our pivot, and this is our force, our weight. So this is the distance we need to use. It's the difference between 1.8 and 1.3, which is 0.5. So it's 3.4 times 10 to the power of 4 times 0.5. This gives you an answer of 1.7 times 10 to the power of, oh, let's just, I don't like that 7. Much better. Times 10 to the power of 4. Newton meters. Because it's force times distance, so the unit is Newton times meter. Okay? Next. A concrete block is positioned on the other side of the support post with its center of mass a horizontal distance of 70 centimeters from the center of the support post. So he's talking about this block over here. State what's meant by center of mass. Another definition question. This is getting tedious. It's the point in an object where the mass of an object is considered to act. Done. The weight of the concrete block produces a moment about point P that exactly cancels the moment caused by W. Obviously, if it's in equilibrium, then the clockwise moment of the signpost is equal to the anti-clockwise moment of the block. Calculate the weight of the concrete block. Again, this is what I just said is basically the answer, or at least the key to the answer. The clockwise moment of the signpost, or the sign, is equal to the anti-clockwise moment of the block, and the pivot is still P. That's our pivot, about point P. So since we already have the clockwise moment, we got it over here. The anti-clockwise moment of the concrete block is this. This is the weight of the block And this is the distance to the pivot. So 70 centimeters, which is 0.7 meters, by the way, and another 1.3. This gives us a total distance of 2 meters. So 1.3 plus 0.7 is 2. So all that we have to say is force times distance, again, is equal to moment. But which moment? The one we just got, 1.7 times 10 to the power of 4. The force is what we're looking for, and the distance, as we've stated earlier, is 2 meters. So 1.7 times 10 to the power of 4 divided by 2. This gives us a final answer of 8.5 times 10 to the power of 3 newtons. Now the block is removed. The sign and the post rotate about point P in the clockwise direction, obviously, because the counterweight is now gone, so it's going to rotate clockwise. State and explain what happens to the moment about point P due to the weight of the sign as it rotates. Now, this requires a little bit of visualization from you. Forgive me, I can't speak today. A little bit of visualization from you. When this entire bloody thing rotates, take a look at this. This is what it's going to look like. Here's the post. Here's the rest of it. And here's the sign. As it rotates to the right, the center of mass of the sign also shifts to the right, which increases the distance between the center of mass of the signpost and the pivot. And if this distance increases, what happens to the magnitude of that moment? It also increases, because remember, moment is force times distance. If the distance increases, the moment increases. The force hasn't changed. It's the distance that's increased. So when he asks me what happens to the moment, state and explain. So the moment increases. Why? Because the perpendicular distance between the center of mass of the sign and P, which is our pivot, increases. And that's pretty much it. Let's adjust this here. Looks fancy. Let's move on. And a cube of side 0.04 meter. A cube. Now this is a keyword that's going to be important later. You'll see why. A cube of side 0.04 meters is floating in a container of liquid. Figure 3.1 shows that the surface of this liquid is 0.028 meters above sea level. Or what sea level? Above the level of the bottom face of the cube. Distance is right there. The pressure of the air above the cube exerts a force on the top face of the cube and the valve is closed. Explain in terms of air molecules how the force due to the pressure of the air is produced. This answer never changes. This answer never changes. So what is it? The reason air or air molecules apply pressure on any kind of surface is because the air molecules move around. What do they do as they move around? They move around freely and collide with the, in this particular case, the top face of the cube. But then when each molecule, bang, collides with the surface, bang, collides with the surface, bang, collides with the surface, every single collision causes the molecules to experience a change in momentum. So the molecules move freely and collide with the cube, experiencing a change in momentum. And remember, the rate of change in momentum is called force. So whenever the momentum changes due to that collision, that applies a force. So applying a force. That's pretty much it. Now, usually a question like this often asks, how does the gas apply pressure? Not how does the gas apply force? So we would just finish this answer off. It would probably be worth another mark. We would finish this answer off by saying applying force over the area of the walls. So we can, upgrade that from force to pressure. But that wasn't required in this particular question. So let's move on. The density of the liquid in the container is 1,500 kilograms per meter cubed. Calculate the pressure due to the liquid at a depth of 0.028. Pressure due to a liquid equation is very simple. Rho GH, density times 10 times height. So 1,500 times 10 times 0.028. I hope I don't sound too weird. I haven't been feeling well lately. Allergies and such. So 420 Pascal. Wait, is this right? Yeah. Okay. So 420 Pascal. Next. The force on the bottom face of the cube caused by the pressure due to the liquid. Now, we do have the pressure now, and he did ask for the force on the bottom face of the cube. If he asks me for force and I have pressure, the answer is quite simple. Pressure is force over area, so force is pressure times area. We do have the pressure, but wait a minute. Do we have the area? I'll go back to the diagram for a second. He did say that this is a cube. So if you visualize this again correctly, this is a cube with equal sides. It's a cube. So 0.04, and this is also 0.04. So the area of this bottom face or top face, I don't really care. The bottom face or the top face is 0.4 times 0.04. I mean 0.04 times 0.04 or 0.04 squared because it's a square, a cube, okay? So the area is going to be 0.04 squared. This gives us a final answer of 0.672 newtons. Or 0.67 newtons, that's fine. Next, the valve is open and the liquid is pumped into the container. The surface of the liquid rises a distance of 0.03. Great. The cube remains floating in the liquid with its bottom face 0.02 below the surface. So nothing's happened to the cube essentially. It's just risen up because the amount of water is increased, but it's still the same depth within the water. Calculate the work done on the cube by the force that you've calculated in BII. Now work is quite simple. Work is force times distance. So it's that same force times the distance that the cube was lifted up. So times 0.034, which gives me 0.0. You've got a really long number here. So I'm just going to write this down to 3 significant figures. So 0.0228. 0.0228 joules. Next one. Suggest one reason why this is not an efficient method of lifting up the cube. Now think about this. Let's delete this. If we're pouring in some water to push the cube up, that's great and all. It's fabulous. You've pushed the cube up. Great. But also don't forget that you've also pushed the water up, which also requires some energy. So a good portion of the energy you used in order to push the cube up was also used to lift the rest of the water up alongside it. So the reason this isn't really efficient is because you're wasting energy lifting the water too. So energy was wasted in lifting the liquid up as well. So it's not just the block. It was the liquid too that was lifted. Capiche? Next. A gas of mass 0.23 grams, let's highlight numbers here, is trapped in a cylinder by a piston. The gas is at atmospheric pressure, which is 1 times 10 power 5, standard really. The volume of the trapped gas is 1.9 times 10 power negative 4. I know this diagram looks a bit, threatening, but don't let it scare you. It's basically just a piston. He's got some kind of catch here just to hold the piston in place, and he drew a symbol for a heater in there. He probably wants to heat the gas and have it expand or have the pressure increase. We don't know. We'll see. An electric heater is used to increase the temperature of the gas by 550 degrees Celsius. Sorry about that. So the specific heat capacity of the gas is 0.72. Calculate the energy required to increase the temperature of the trapped gas by 550. Since he's given me the specific heat capacity, my mind immediately goes to our good old standard energy equation, mc delta T. And he wants the energy. So do we have the mass? Yes, we do. 0.23. Do we have the specific heat capacity? Yes, we do. 0.72. And you'll notice that they're both in grams, so I'm not going to change any units. And the temperature increased by 550, so we'll also leave this as is, which gives me an answer of, let's plug these into our calculator here, of 91.08, so just 91.1 joules. Fantastic. The power of the heater is 2.4 watts. Does he want time now? Yeah, he does. Calculate how long, as in time, does it take for the heater to supply the energy calculated in AI. So do remember that power is energy per unit time. So if you do want the time, time is energy over power. The energy is 91.1 divided by 2.4. I'm just going to divide my previous answer by 2.4, which gives me 37.95. So if we round this up to 3 significant figures, it just gives me a solid 38 seconds. We're using SI units here, folks. In practice, it takes much longer to increase the temperature of the gas by 550. Ooh, I wonder why. Why would it take more time to increase the temperature of the gas by 550 using this heater? So just one reason for this. Now, please keep in mind, when you're heating the gas, who said all of the heat is going to the gas? Don't you also lose some of the heat to the piston or to the surroundings? Which means you don't really only heat the gas, you also waste some of the energy heating the surroundings and heating the piston and heating the cylinder and everything else. So you lose some of the heat to the surroundings or the cylinder or the piston. So some heat energy is lost to the surroundings. Done. When the temperature of the gas is increased by 550, its pressure is 2.9 times 10 to the power of 5. The catch is then released. So remember, now this pressure is really high, and you've released it. So this piston is going to move out because the pressure inside is greater than atmospheric. Remember, atmospheric is 1 times 10 to the power of 5. So yeah, it's going to move out. So Satan explained what happens to the piston. Oh yeah, he did also mention that the temperature remains constant. So what happens to the piston? Well, it moves out, it moves to the right. Why? Because the pressure of the gas inside is greater than atmospheric, than the pressure on the right side. So the piston moves to the right because the pressure of the gas inside the cylinder is greater than atmospheric. Determine the volume of the gas when the piston stops moving. Now, if we already have a final pressure and we have an initial pressure, which was the atmospheric pressure, that's before I heated the gas, and this was the initial volume of the gas. I apologize. This is the final pressure, my bad. This is our final pressure because this piston is going to keep moving out until the piston stops moving. The only reason the piston would stop moving is if the pressure inside and outside are the same. So that's our final pressure, atmospheric, P2. That's our initial volume, V1. This is our initial pressure, P1, before we release the catch. The moment you see P1, V1, and P2, V2, we have our equation ready. P1, V1 equals P2, V2. P1 is, my memory fails me, 2.9 times 10 to the power of 5. Times V1, which is on the previous page, that's a 1.9 times 10 to the power of negative 4. Equals P2, which is atmospheric, because again, the piston expands until it stops moving. So 1 times 10 to the power of 5 times V2, which is what we're looking for. Remember, V2 is supposed to be greater than V1. So just work these out on your calculator. Plop, 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 plop. Plop these numbers in. Let's plug them in now. Times 10 to the power of 5 times 1.9, 10 to the power of -4, divided by 1, 10 to the power 5. This gives me a nice 5.51 times 10 to the power of -4. And the unit is obviously meter power 3, or meter cubed. Meter cubed. Next, liquids and gases are two states of matter. We know. In both evaporation and boiling, a liquid changes to a gas. State two ways in which boiling differs from evaporation. This one is a simple question, though. Boiling only happens at the boiling point, so that's a specific temperature, whereas evaporation happens at any temperature. That's one good difference. Another difference is that boiling occurs throughout the entire liquid, but evaporation only happens to the surface molecules. That's another thing, right? So let's just use those. So boiling occurs at a specific temperature, which is the boiling point, but evaporation happens at any temperature. Rupture. There we go. And the second is what? Boiling happens throughout the whole liquid, but evaporation occurs on the surface only. So liquid evaporates from the surface, whereas boiling happens throughout the entire liquid. Boiling happens at a specific temperature, which is the boiling point, by the way. You can just say boiling occurs at the boiling point, but evaporation happens at any temperature. Before injecting a patient, a doctor wipes a small amount of volatile liquid, alcohol or ethanol, on the patient's skin. Explain in terms of molecules how this procedure cools the patient's skin. Now, he's obviously talking about evaporation here, like our hint was basically the previous part. So when the liquid molecules evaporate, like the most energetic molecules on the surface of the liquid break their bonds and escape, what do? They leave behind less energetic molecules. Because the molecules left behind are less energetic, the temperature of the liquid will decrease. And that liquid will absorb heat from the patient's skin, cooling it down. So we'll just mention the most energetic molecules escape from, molecules escape from the liquid, leaving behind less energetic molecules. So the temperature of the remaining liquid decreases, which then absorbs heat from the patient's skin. Great. Next. Gases can be compressed, but liquids are incompressible. Explain in terms of molecules why liquids are incompressible. Now, liquids are already really close to each other. Like they already have very small spaces between them, and their intermolecular forces are relatively strong. Like they do have very strong forces. So if you try to force them close to each other, they're already close. They don't need to move any closer. And they already have strong forces between them. And if you try to force them even closer, they'll start repelling each other. That's not a good idea. So all that we'll mention is there is very little or little to no space between the molecules, and they have very strong, or just strong, I'd rather just say strong intermolecular forces. Boom. Gases have none of those, so gases have very large spacing. Next up, green light of frequency 5.7 times 10 to the power of 14, highlight now, is traveling at an air speed of 3 times 10 per 8. The light incident on the surface of a transparent block. So it's incident on this block over here. Figure 6.1 shows the wave fronts in the direction of travel of the light in the air. Blah. The light travels more slowly in transparent solid. Duh, we know that, but he has to emphasize that. Explain in terms of wave fronts why the light changes direction as it enters the solid. You may draw on figure 6.1 as part of your answer. Now, I'm not going to draw, I'm just going to draw so I can just point something out. When this wave front hits this medium, hits this surface, hits this boundary, part of it is inside the solid, but the other part is still in the air. The part of the wave, or the part of the wave length, the wave front, that goes into the solid surface slows down, as he said. But the part that's still in the air, still moving pretty fast. Because of this difference in speeds for the same wave fronts, the entire wave front or wave starts to bend. So the whole idea is what? That part of the wave front hits the surface first, or hits the medium first, or hits the solid first. So it slows down before the other side. So the entire wave bends and changes direction. So that's our answer. So part of the wave front hits the solid before the rest. So it slows down first. This causes the wave front to change direction. You can changes its angle and so on. Next, the refractive index of a transparent solid is 1.3. Thanks for the end, man. And oh, where's my highlighter? There it is. The light incident on the surface of the solid is 67 degrees. Calculate the angle of refraction. So n equals sine I over sine R. I prefer sine air over sine glass because it's always preferable if you have the larger angle up here and the smaller angle down here. So it helps with your workouts. Because sometimes it's not the incident angle that's in the air. Sometimes it's inside the solid already. So 1.3 is sine 67 divided by sine R. So this means that sine R is equal to sine 67 divided by 1.3. Once you plug this into your calculator, shift sign your answer. So on your calculator, there's sine power -1. So shift sign your answer so you can get the degrees, the answer in degrees. So 45 degrees. Make sure your calculator is set to degrees, okay? The unit for angle is degrees, not radians, not radians, degrees. Determine the wavelength of the green light in the transparent solid. So wait, how do we get wavelength in the transparent solid? 4 marks! What are we gonna do? Well, first things first, let's think slowly. If he wants wavelength, and we have the speed of the wave, or do we? If we can get the speed of the wave, and we have the frequency of the wave, it's right up there, we can get the wavelength using V equals F times lambda. Oops, F lambda. But the problem is we don't have the speed of the wave in the solid. We have the speed of the wave in the air, 3 times 10 power 8. But wait, that's why we have the index. That's why this is B double I. It's part of the same question. Remember that the equation for the index is not just sine the angle in air, sine the angle in glass, or sine I over R. It's n equals the speed of the wave in the air, or speed 1, over the speed of the wave in that second medium. So if n is 1.3, and the speed in air is 3 times 10 to the power of 8, the velocity that you're looking for is 3 times 10 power 8 over 1.3, which is 2.31 times 10 to the power of 8. So it has slowed down. Now that you have the velocity and you have the frequency, which is, once again, 5.7 times 10 power 14, you can just plug these in. So 2.31 10 power 8 equals 5 point, what was it again? Oh gosh, why do I keep forgetting so quickly? 5.7 times 10 power 14. That's our frequency times wavelength. So the wavelength is this over that. 2.31 times 10 to the power of 8 divided by 5.7 times 10 to the power 14. This gives me a final answer of 4.05 times 10 to the power of -7. Mind you, a question like this has multiple approaches. Like there are other ways to get the answer. They're all fine. This is just one of those ways. Moving on. Figure 7.1 shows a circuit diagram that includes component X. State the name of component X. Well, that's easy. This is a thermistor. So, next. The electromotive force, EMF, of the battery is E. The switch is closed. The potential difference across the 30 ohm resistor is V30. Across the 20 ohm resistor is V20. Across X is Vx. State an equation that relates Vx to V30. Okay, wait just a second. Vx is this. And V30 is this. Oh wait, they're parallel, which means they're equal. So Vx is equal to V30. Easy enough. Next, he wants an equation that relates E, which is the EMF of the supply, Vx and V20. So what's the relationship between these two? Well, Vx plus V20 gives you what? E. So if this was 10 volts, for example, and this was 2 volts, this would be 8. So E is equal to Vx plus V20. Okie dokie. Next. The EMF of the battery is actually 6 volts, and the resistance of X is 15 ohms. Calculate the total resistance of the circuit. So now we actually have a value for this. So this is 15 ohms. So first things first, these two are in parallel, and then we have this 20 ohm in series. So let's first calculate the combined resistance of the 30 and the 15 ohm in parallel. So we do this using product over sum. So first, the resistance of the parallel components. So 15 times 30 over 15 plus 30. This gives me no, I don't want standard form. 8 to 10. And then, since this is in series with the 20 ohm resistor, this means that the total resistance is 10 plus 20, which is 30 ohms. Fabulous. The ammeter reading. Okay, is the ammeter reading anything specific? Yeah, the total current. So that's cool. So I equals V over R, with the total voltage being 6 volts and the total resistance being 30. So 6 over 30 gives you 0.2 ampere. Next up, the temperature of component X increases. What was component X again? It was a thermistor. And if the temperature of a thermistor increases, its resistance will decrease. Now let's move on back to the question. State and explain what happens to the ammeter reading. Oh, this is cool. So if the temperature of the thermistor increases and its resistance decreases, this means that the total resistance of the circuit will also decrease, which will increase the what? The current, therefore increasing the ammeter reading. So as the temperature of X increases, its resistance decreases, which decreases the total resistance in the circuit. Right. So if the total resistance circuit decreases, the ammeter reading then increases. Because the current will increase. Next up. The student turns the handle of an alternating generator and the coil rotates. Figure 8.1 represents the structure of the AC generator. So here's the coil. Remember, the generator is when we, spin a coil inside a magnetic field, or we move a wire through a magnetic field. And as the wire cuts through the field, you induce a current or a voltage or an EMF through the coil or across the coil. There's an alternating voltage output between the two terminals. Explain why rotating the coil produces an output voltage. So as we just mentioned, when you rotate this coil, what does it do? It cuts through the magnetic field. And as it cuts through the magnetic field, you induce a voltage or a current. So as the coil rotates, it cuts through the magnetic field of the magnet, inducing a voltage in the coil or across the output, so that's fine. State the position of the rotating coil when the alternating output voltage is at maximum, and explain why the maximum output occurs at this position. Now, just to remind you, the maximum voltage is achieved when the coil is horizontal, because at this moment, the ends of the coil, which are the wires that are doing the cutting, are moving up and down, which is perpendicular to the direction of the field. But, if the coil was vertical and the ends of the coil, which are the two wires, are moving parallel to the field, this gives you a voltage of 0. So remember, you get the maximum voltage when the coil is horizontal, because the ends of the coil, the wires, are cutting the field in a perpendicular direction. Whereas this coil, when it's vertical, when the coil is vertical, it doesn't generate anything. It gives you 0 volts because it's parallel to the field, because the ends of the wire are parallel to the field. So state the position of the rotating coil when it's at maximum, so horizontal. Why? Because it cuts the field at 90 degrees, or it's cutting the field the fastest, because when you're at 90 degrees, you're moving very quickly. When you're at an angle, you take a slightly longer time to travel between field lines. And when you're parallel, you're doing nothing. So when the coil is horizontal. Because the coil cuts the field the fastest. Or because the coil's wires are moving perpendicular to the field. A lamp and an open switch are connected in series to the output terminals of the AC generator. The switch is closed and the lamps light up. The student has to apply a greater force on the handle. Explain why a greater force is needed to keep the lamp lit. Now, keep this in mind. Initially, this wasn't connected to anything. You just had a voltage, so you weren't really required to deliver any specific power to the lamp or otherwise, to anything. But when you start connecting something here, a lamp, this requires power now. This requires a current, which means you need to up the current generated by the coil, which means you need to start spinning it faster, because you need to start supplying more energy. So because you're delivering energy to the lamp, you need to do more work to generate more energy, which is why you need a greater force. So let's type this up. The energy has the switch is closed and the lamp lights up. So we'll say that energy is now being delivered or supplied to the lamp. So the student needs to increase his force or her force to do more work and supply that extra energy or work. Next. I think this is the last question, right? Yeah, it's a total of 9 questions. So this is an atomic physics question. This is the alpha scattering experiment. So figure 9.1 shows a beam of alpha particles moving towards a thin sheet of gold in a vacuum. Detectors in the region surrounding the thin gold sheet detect the alpha particles and determine the number of particles that travel in various directions. State and explain what can be deduced from the following observations. So, okay, there were 3 observations if you remember. Most of the alpha particles go through the foil or the gold sheet undeflected. That's because the nucleus inside is extremely small and the atom is mostly empty space. So the alpha particles don't really hit anything. Then some of the alpha particles do change direction because they move close to the nucleus, and the nucleus is positively charged, so it gets, repelled. And then an extremely small number get repelled backwards or deflected backwards because these alpha particles hit the nucleus, but because the nucleus is very dense and it has a lot of mass, it doesn't move. The alpha particles move. So that's basically the answer to this question, but let's go ahead and read it first. State and explain what can be deduced from the following observations. The majority of the alpha particles pass through the gold sheet undeflected and are detected on the other side. So what can we deduce? We can deduce that the nucleus is extremely small in size. Why? Because most of the alpha particles didn't hit anything, or were far away or moved far away from the nucleus. So that's kind of why. That's why most of them went through undeflected, because they didn't hit anything. A small number of alpha particles are deflected as they pass through the gold sheets. The reason they're deflected is because the nucleus has a positive charge. Why did we figure that out? Because when the alpha particles move close to it, the alpha particles that move close to the nucleus experience a repulsive force. So just get repelled. That's why they change directions. And finally, a very small number of alpha particles are deflected through very large angles, or basically return back from whence they came. Oh, okay, that sounded ominous. But why do they go back? Why do they get repelled? Because these alpha particles hit the nucleus, which means that the nucleus has a lot of mass, or basically all the mass, almost all the mass of the atom. What's the explanation to that? Because the alpha particles hit the nucleus move, but the nucleus doesn't. Think about this. Think about this. If the nucleus wasn't massive, if it didn't have a lot of mass, or if it wasn't dense, and the alpha particle hits the nucleus should have been knocked out like a billiard ball, like boom, just moves away. Why? Why didn't it do that? Because it's basically you using a ping pong ball to hit a bowling ball. It's extremely heavy. Most of the mass of the atom is in that nucleus, so the nucleus doesn't move. That's why the alpha particles go back. A beam that consists of both alpha and beta particles is passed through a region of space where there's a magnetic field perpendicular to the direction of the beam. State two ways in which the deflection of the alpha particles differs from the deflection of beta particles. Now, if you remember, if we have a magnetic field into the page, like its direction is into the page, and you have both alpha and beta particles traveling along the same line, using Fleming's left-hand rule, you'll realize that the alpha particles experience an upward force, so they deflect upwards, but the beta particles would deflect down. But there are two major differences here. First, the direction. The alpha and beta particles move in opposite directions. And second, that's because they're oppositely charged. And second, the beta particles deflect more than the alpha particles. They change direction more. Why? Because they have less mass than an alpha particle, so they're easier to move around and to bully, basically. So the alpha and beta particles move in opposite directions, and the beta particles deflect more than the alpha. or deflect in opposite directions and so on. Okay. And I think that's pretty much it. That's the end of the exam. Yeah, that's the end of the exam. I hope you found this useful, and good luck with your exams. Have a wonderful day, evening, night, and goodbye.